So I think last time we stopped over here. We briefly mentioned the definition of fugacity. So if you're dealing with ideal gas, and if you want to calculate the change of Gibbs free energy, you use this equation. And because for ideal gas, this can be replaced by the ideal gas law. Therefore, V is RT over P. So for ideal gas, this is simply this expression. Therefore, for ideal gas, we can directly use d log P to calculate the change of Gibbs free energy. However, if you're dealing with non-ideal gas, then you cannot change from V to RT over P. But sometimes we still want to use this expression. So for non-ideal gas, they define a different function called F, which is the fugacity. And this is similar to what pressure is over here for the ideal gas, but this is a function of pressure. And of course, the value will be different from the value of pressure. So in fact, if you know the relation between this fugacity and pressure, then you can also use this to calculate, for instance, the change of Gibbs free energy. One of the examples is that you can change this to something like this. Later we'll see that. Actually, we already saw this last time, that the textbook gave this definition first, and then later defined something like this, which allows you to calculate for the non-ideal part of the gas. And this is the ideal part of the gas. So this part is the same as the ideal gas expression, but for the non-ideal gas, or for the real gas, you have this extra term. And you can see that if you combine these two, you'll go back to the original definition of fugacity. So this equation is important for its definition of fugacity. So this is the so-called the second way, or you can say this is the first way of calculating the change of Gibbs free energy for the real gas, if you know the expression for fugacity. But most of the time, this is unknown. Therefore, like I mentioned last week, that you have to go back to the original definition. So we know that this is always true, right? If you're dealing with a process that is under, say, constant temperature. If it's a constant temperature process, and the only change is like either the pressure or the volume, then you use this expression. And as long as you know the volume as a function of pressure, then you can use this equation to directly calculate the change of Gibbs free energy. So this is the first way. The second way, let's say, you just go back to the original expression. And in some cases, for instance, if you're dealing with the Virial expansion, like we show over here on this slide, we know that for Virial expansion, PV over RT is a function of pressure. So by moving the part with pressure to the right-hand side, you can have an expression of a volume as a function of pressure. So this one, the second equation. So once you have this expression, we know that this volume is a function of pressure. Then you can directly calculate this by simply integrating over the range that the process is about. Right? For instance, if you're dealing with, and we know this is from, for instance, from P1 to P2. Then you can do this calculation. So actually, for most of the time, you're going to use this to calculate the change of Gibbs free energy instead of using the fugacity. But since the textbook spends a lot of time, several pages discussing fugacity, so that's the reason why we also write this out. Okay, so this part is about evaluation of dg, or the change of Gibbs free energy. And of course, like the method I mentioned over here, you can start from the definition. dg is vdp, so if you still cannot remember, recall that this is minus dt plus vdp. And since we're dealing with constant temperature process, so this term is 0, because this is constant. Okay? If you're not dealing with a constant temperature process, so you're going to change the temperature, then you have to include this term. Okay? But right now, we're just dealing with constant temperature. Since starting from the beginning of this chapter, we're talking about isotherms, right? Which means that the temperature is constant. Okay, so this is the most straightforward way to calculate change of Gibbs free energy. And if you're dealing with a Virial expansion, this is the expression for volume as a function of pressure. So if you do the integration, like I mentioned over here, this will be the final expression of what the Gibbs free energy change should look like. So if you look at this expression, you'll see that if the gas is ideal, so if you're dealing with ideal gas and there's no higher order terms, which means that there's no, so B is 0, C is 0. Let me do this. So B is 0, C is 0, and D is also 0, which means that the gas is ideal. And if that's the case, then you're left with only delta G's RT log P2 over P1. And that's exactly what you will get if you're using this ideal gas expression, right? Because you don't have all those extra terms. And the rest of the contribution is from the non-ideality of the gas, which means that only when you're dealing with real gas you have these terms. And it depends on how many terms you want to include. For most cases, you probably only include the term with prefactor B. So you only include this term, and the rest are not that important, especially when you're dealing with low pressure calculations. And of course, the second way, or the first way I mentioned here, is to start from the definition of fugacity. You start from here, RTD log F. And of course, RTD log F can be decomposed into these two terms. So we'll see that this part is the same as the ideal gas part, and this part is related to the non-ideality of the gas. So from this expression, you can suddenly know that this should be the same as this term, right? Because the first term is RT log P2 over P1, and that corresponds to this. And here is the non-ideal contribution, and here is the original ideal gas contribution. So imagine that if, like I mentioned earlier, that these prefactors, like if you're dealing with ideal gas, and B and C and D, these are all zeros, so you don't have these terms, then if you're using this expression, it means that F over P must be 1. So the fugacity and the pressure are the same, and so the non-ideal part is vanished. So you are only left with the ideal gas part. So essentially these are the same. Okay, these things are the same. But of course, last time we spent some time talking about this calculation of log F over P. So that's the reason why over here we can just plug in this expression. If we want to calculate log F over P, we can plug in this expression and then combine that with the rest of the, the ideal gas part. So the textbook went through this calculation. Since we already know the expression of Z, right, because we know the Virial expression, this is 1 plus B plus da. So you know how to calculate Z minus 1 over P. So if you do that, you'll suddenly see that this is the same as integrating over these non-ideal terms. So it turns out to be BP plus like CP squared over 2 plus the rest of the terms. So if you combine this with the ideal part, so what we just calculated is this part, and if you combine that with this term, then you'll see that it's the same as what we just derived, right? This is the same as you're starting from directly the expression of VdP. So these two are essentially the same. So don't be confused by textbook. It sort of like goes back and forth, but if you always start from these two definitions, you can get the correct result. So I believe either one of them will be in the final exam. I think probably this one or this one. I mean, this what typically shows up in the numerical calculations. So I'll give you the expression of volume as a function of pressure, or give you, later we'll see some examples, some gas laws, either Virial or van der Waals gas. And you can express volume as a function of pressure, and then you can calculate this. And later we'll see more like mathematical tricks. Actually, there are some mathematical tricks to simplify the calculation of change of Gibbs free energy. However, I don't see any problems using fugacity, but this is what you probably will encounter during the next semester if you're going to continue studying thermodynamics next semester. You will encounter fugacity again. So this is the expression that probably not very useful right now, but you'll see that later. Okay, so two approaches. Please bear in mind. Okay, so the number of terms which must be considered in that Virial expansion really depends on the magnitude of range of pressure, like I mentioned earlier. So if you're dealing with a low pressure range, for instance, it's close to 1 atm, then you'll probably only need to consider the very first two terms, okay, or only the first term. For example, for nitrogen gas, empirical expression is that PV over RT is 1 plus BP plus CP2 plus DP3. But if you're using just the range of 6 atm, you only need to consider this very first term. Okay, so for low pressure, the linear trend or the first linear term is already good enough to mimic the real gas behavior. So if you still remember from last time, we've seen this kind of plot. If you plot Z as a function of pressure, it's typically something like this. So it means that if you're in the low pressure regime, you should be able to use just a linear approximation. Therefore, Z is 1 plus BP, right? So you only need the first term. And of course, here is 1. We know that when the pressure is 0, this factor Z should be close to 1. So in the case of nitrogen, you only need these first, well, this is the first term, this is a constant term when you're at low pressure. So in that way, if you move terms around, the volume can be expressed as RT over P plus BRT. So if you recall that from last time, actually at the very, very beginning, we have this weird expression. V, volume is RT over P, and we call this the deviation from the ideal gas rule. So it turns out that if you're using Virial expression, this term, alpha, is simply minus BRT. Okay? So I'm not sure why the textbook was jumping back and forth using different kinds of expressions. But at least over here, I think it is more straightforward. So typically, my preference is that I always start from the Virial expression, because this is a very general expression, and it allows you to think about the trend of this function z as a function of the pressure, and also you can use that to derive a lot of things that previously were using some weird terms to derive. For instance, right now we know that if you express volume using the Virial expression, and it turns out to be having this ideal gas term, RT over P, plus this non-ideal deviation. And therefore, that alpha of T that we saw earlier is actually minus BRT. And you can see that it's indeed a function of temperature. Okay, it's indeed a function of temperature. So it means that if you're dealing with a Virial expression and you only use this first term, this first expansion, only consider this linear term, this volume is simply the ideal gas term plus this temperature-dependent term. And therefore, you can imagine that if you plot the PV isotherm, it's simply a shift by a certain amount. Because we know that if you're dealing with ideal gas, this is RT over P. This is ideal gas. But right now, the volume is actually plus this. This is non-ideal gas, and or using a Virial expression. So it's simply this value shifted by a certain amount. So if you look at the PV plot, okay, the PV plot, the left, the one on the left-hand side, this one is the ideal gas, original ideal gas isotherm. But if you're now considering this isotherm with the non-ideality being considered, then it simply shifted the volume by the number of BRT, this one. So it simply means that the line has been shifted by this amount. Okay, and it is a direct, horizontal shift. So if you're dealing with, right now, for instance, we want to calculate the work done by this non-ideal gas. You'll see that if you have the same pressure change, okay, so if you start from pressure 1 and then you decrease the pressure to pressure 2, and because if you decrease the pressure, it means that the volume has been expanded. So this gas will do work on the outside, and if you integrate this volume out, this is the volume represents the work done by the system, by the sponge of gas. And if you have experienced the same pressure change for the non-ideal gas, the volume underneath these two curves will be the same because you simply shift that area by the same amount by this BRT. So if you're dealing with a simple pressure change from P2 to P1, and if you want to calculate the work, for ideal gas, it is this volume. And for non-ideal gas, it's the same. Oh, sorry. These two, they're not that similar on Blackboard, but on the textbook, it looks more like the same. Because this curve is simply the ideal gas isotherm shifted by BRT. And of course, if the temperature is higher, you can expect that this shift between these two lines will be more and more significant. But this is the case when you perform this process from P2 to P1, which means that these two processes are having the same pressure change. However, in most cases, you're dealing with how to say that? We control the volume instead of the pressure. So for instance, if you're changing the gas, say from V2 to V1, if you have the pressure change from here to here, then of course for ideal gas, the volume, the area underneath is still the same. So this is the work done by the ideal gas. But for non-ideal gas, these two lines should go up. So you have to consider this whole area underneath, which means that if you have the same volume change, the ideal gas will do less work than the non-ideal gas, right? Because for non-ideal gas, you can imagine that the volume is, say, IJ dA, like if you move from volume 1 to volume 2. But for ideal gas, it is BC dA. So it is only this area underneath. So depending on the constraints, if you're dealing with the change from volume 1 to volume 2, then non-ideal gas will do more work than the ideal gas. However, if you're dealing with the same pressure change, say from P1 to P2, then these two gases will have the same work done to the outside. Okay, so depending on the constraints, the result will be different. So here, like the first scenario I mentioned, you consider a reversibly isothermal expansion from P1 to P2 at constant temperature. Of course, these are isotherms, so we're always dealing with constant T. So on this PV diagram, then we know that this is only a shift of this isotherm by amount of BRT. Therefore, the area will be the same because if you imagine the pressures are the same, these two areas will be the same. And this, of course, can be calculated directly. If you use ideal gas to calculate, we know that the area underneath is calculated by PdV. So it turns out to be, for ideal gas, this can be directly replaced by RT d log V, right? So it turns out to be something like this. For non-ideal gas, of course, we don't know what's the change of volume, right? At this point, the problem gives you the change of pressure. So for non-ideal, you know that we want to calculate PdV, and from, let's say, V1 to V2. I think I should exchange these from P1 to P2. And let's say this is V1 prime, V2 prime. So in the case of non-ideal gas, actually we don't know what V1 prime and V2 prime is. We only know that, okay, so pressure is P1 to P2, but we don't know exactly what V1 prime, V2 prime is. So we have to do some mathematical trick. So for instance, the trick done over here is that we first replace this dV by using the gas, the expression of the Virial expression. The volume is RT over P plus this BRT, right? We've already mentioned this. And we take the derivative of this volume. So we want to figure out the expression for dV such that we can plug in over here. So it turns out that dV is minus RT dP over P squared. So this is a general trick that we'll encounter later, that we want to calculate this, but we don't know how to do this part. So we'll replace dV with dP. Or to be more precise, we replace this with so this is a very general trick that we will see maybe maybe 1 or 2 times later. So again, sometimes, so this is a general trick, that you want to calculate something that is related to dV, and then but you don't know how to calculate this. For instance, we don't know how to calculate the change of from volume 1 to volume because we don't know what volume 1 prime is and volume 2 prime is. But we know the pressure. So we want to change the variable into pressure. So if that's the case, we typically will replace this to and the reason why we can have this is because we're mostly dealing with constant temperature process in this chapter. So we have this partial V, partial P at constant temperature. And you'll see that this is related to this is compressibility, right? This is related to alpha or beta. Yeah, I don't remember. We'll see that later. But once you know the expression of V as a function of pressure, then you can express this. Or you can calculate this. For instance, in this case, we already know that a volume is a function of pressure like this. So under constant temperature, we don't have to worry about this term. And we don't need to worry about this part. So partial V, partial P. So this is P minus 1, so we have minus 1 here. And then P minus 2. Therefore, this is minus RT over P squared. So that's the reason why here you have this minus RT over P squared times dP. Right? Because once you have this, you can plug this back in. So it turns out that this is, let's say, and this is from P1 to P2. And of course, the original constraint, I mean the limits are P1 and P2. So these two numbers are given. So we know what these two numbers are. So that's the reason why we want to change the integration over dV to dP, and then use this to replace that. And this is from the known expression for volume as a function of pressure. And therefore, we only need to plug this back into here. So this is let's say minus RT, P1 to P2. Did I miss something? There's a P over here. Sorry. I forgot the P over here, so here's a P. So it turns out that this is simply d log P. So you see that this is exactly the same as the ideal gas result. And since we're moving from P1 to P2, this is and the minus sign will give you the change between numerator and denominator. So this is the same as the ideal gas result. Okay. So the bottom line is that we'll use this kind of trick, not a lot, but you'll see this quite often. Okay. Especially when you don't know how to, how to calculate the integration, and this trick will be really useful when you don't know how to deal with the problem. Okay, and so here is just to verify that what we intuitively guess over here is correct, right? Those two volumes should be the same. But instead of using this kind of graphical argument, we can directly calculate that, although it seems to be more complicated. Okay, it seems to be more complicated. And the second scenario is that we perform this kind of expansion from V1 to V2. Okay, so it's a different kind of process because now our constraints, or the limits, are volumes. So we're going to move from V1 to V2 for two gases. And of course, the starting pressure and the ending pressures will be different for these two gases because we know that for ideal gas, the starting pressure will be higher, the ending pressure will also be higher. And we also know that from the graphical representation that the work done by the non-ideal gas will be greater than that for the ideal gas. But of course, we also want to calculate that numerically. So this is a way to see that the volume change is the same. So let's say that that factor can be ruled out. However, if you look at the pressure difference, if you use P non-ideal minus P ideal, you'll see that this is a positive number. Therefore, if you integrate over a certain range of volume, you'll see that this will still be a positive value, which means that the work done by the non-ideal gas is greater than that for the ideal gas. So for ideal gas, again, we know that this is the same as what we saw earlier. This is just a simple isothermal expansion, therefore RT log delta V. But for the non-ideal gas, we use the same expression. And then since we already know, again, like pressure is a function of volume, so this time we can calculate it directly. Right? Because right now we're not integrating over pressure because now the variable given by the problem is already volume, right? From V1 to V2, so you can directly plug in. So for this case, it's actually more straightforward. It's easier to calculate. Therefore, if you plug in, since you already know what V1 and V2 is, you can just use this expression to directly integrate over dV. And this is a very simple integration. It will just give you log V or V minus BRT. And therefore, this is greater than the ideal gas work. Of course, if you just directly look at this, it's hard to just compare. Because for ideal gas, we know that this is from V1 to V2. The work done by that is, and for non-ideal, it's also a very simple expression, but from graphical representation, we can easily see that this is greater than this one. But if you just look at the mathematical expression, it will be hard to just compare, right? If you want to compare these two numbers, you probably have, for instance, let us imagine that this is greater than this one. So we want to argue this is greater than 0. And if you do the subtraction, this one minus this, this term minus this term will be this times the inverse of this one, right? Because if you have put a minus sign here, this is simply by replacing the V2 and V1. So this is this will be what you get. And for this term to be greater than 0, I mean this whole thing to be greater than 0, we know that we need this one to be greater than 1, right? This inside, I mean this term. If this product over here is less than 1, we know that this will be a negative number, right? So this is what we're going to argue. And it is obvious that, this, let's say, typically, if you use a real number, maybe this is easier. Like this is, we know that V1 is, if you look at the graph, V1 is smaller than V2. So let's say this is, say 10, this is 5, or this is, let's say 6. Maybe like this, and maybe something like this. And therefore, so we're all okay, right? Of course, you can argue this more rigorously to show that this number is always greater than 1, but typically you can just plug in some numbers to do a sanity check to make sure that this is greater than 1. Yeah, I think I'm correct. So if this number, this product is greater than 1, then it means that if you take log, this is greater than 0. This is a positive number, so this is okay. So we'll check this is good. Okay, so this part is just trying to show you that for different kinds of constraints, you have to use different ways to calculate. Here it is VdP, right? So it is either from P1 to P2 or from V1 to V2, depending on the constraints given. If it's from volume 1 to volume 2, so you better change this to, sorry, it's the opposite, sorry. So if your constraint is volume 1 to volume 2, then this is okay, but if it's from pressure 1 to pressure 2, you have to change this variable to pressure by using the trick that I just mentioned. So in the case of Gibbs free energy, we know that this is VdP, and therefore for calculation, it's the other way around, right? It's the other way around. So this is flipped. So if you're dealing with from pressure 1 to pressure 2, this might be easier to calculate. But if the constraints are from volume 1 to volume 2, then you have to change this term. So it's the other way around. Okay. So the numerical example in this textbook is actually pretty problematic because there are a lot of typos. But I believe that I already fixed most of the typos here. So this is I think the first quantitative problem in your textbook. So it's by considering a van der Waals gas. So consider nitrogen, behaves like a van der Waals gas, and typically, like I mentioned earlier, that if you're dealing with van der Waals gas, the problem will give you the value of A and B, such that you can directly plug in those numbers. So if you recall that for van der Waals gas, you have this gas law, this expression, right? But if you look at your textbook, or if you have your textbook with you, you'll see that for this problem, it gives you a different kind of expression. I think on the textbook, the A over here is A squared, which is pretty odd because if you look at the given constant over here, like A is roughly 1.4 liter square ATM per mole square. So that corresponds to just A over here. If you use A squared, the unit won't fit. So if you look at, if you're using the sixth edition, it's on page 261. And you'll see that for this, on the textbook, the V squared is, the factor here is A squared, which I believe is wrong because here you have minus B. If you're dealing with this expression, you have to look at the, please check the units. And we know that, so here A is 1.39 liter square mole square. So on textbook, I think it is wrong. It places A squared over here. But if you use A squared, then the unit will become liter to the 4 square molar to the 4. This unit is not going to be canceled out with, well, if you use volume square over here or molar volume square over here. So molar volume means it's liter over mole, and square that. So you're left with liter square and a mole to the 2 over here. Right? And also you have ATM square, which means that there's a pressure square for this unit, which I believe is wrong. So if the problem gives you A as a unit of liter square, ATM mole square, then I believe you can only place A over here. So it's not A squared. But unfortunately, for the rest of the calculations in this textbook, it continues to use A squared, even for those integrations. So I don't think the values given in this textbook is correct. But the bottom line is that if you change the expression, if you only want to just calculate this analytically, you don't want to calculate the numbers, you can just ignore this fact. Okay? But if you want to calculate the correct number, you have to use A. You have to use A. Okay? So in the case of using A, this is more straightforward because we know that if you're using A, this is liter square ATM per mole square. So these will cancel out, and you're left with just ATM, which is the unit of P over here, which means that this is the correct expression. So please, if you want, can change that on textbook. But there are tons of that to be modified. So because from page 261 to 263, all those A's are represented as A squared. So if you want to change that, you have to change all of them. Okay. But nevertheless, on the slides, I change all of them into A. Okay. So the problem gives you this kind of constraint. The volume will be expanded from 1 liter to 2 liters at a constant temperature at 400 Kelvin. So it asks you to calculate the change of Gibbs free energy and the change of entropy. So this is, these two quantities are the common guests in this chapter. So you'll see later there are more problem sets at the end of chapter 8, and they're all asking you to calculate the change of Gibbs free energy and the change of the entropy. So the change of Gibbs free energy is much easier because we already know the expression for dg is VdP, right? We've already seen this 1,000 times in this chapter. The problem is how to calculate delta S. And at the very beginning, if you don't remember from chapter 5, then it will be really hard to calculate. But if you know from chapter 5, we derive like there are 2 TdS equations, and one of them is like this. So TdS is this CP/dT minus a term that is related to alpha. And it turns out that this expression is very useful because if you're dealing with constant temperature process, the first term on the right-hand side will just disappear, right? This term will just be 0. So if you move temperature to the right-hand side, and you can eliminate one temperature over here, so you're left with just minus alpha V times dP. So if you don't want to derive that, you can just, if you can memorize this, just be my guest. So the bottom line is that in this chapter, typically if you want to calculate the change of, the change of Gibbs free energy, you use this expression. And if you want to calculate the change of entropy, then you use this expression. Okay, and alpha here is the I think I have it here. Is the thermal expansion coefficient. Okay, the alpha here is the thermal expansion coefficient. So you see that there are a lot of things that you need to work on if you want to calculate delta S. First of all, you have to derive, not to derive, but you have to know the explicit form of alpha, for that certain gas, right? Such that you can plug in and then do the calculation. Unlike for Gibbs free energy, it seems to be much easier because if you know the expression of volume as a function of pressure, then you can directly calculate that. But that's just the only, the first step. Because like I mentioned earlier, this expression is only good for the variables that you're using are for instance, if they are pressures, then this one should work. But if you're dealing with a volume change, for instance, in this case, the constraints or the limits are from 1 liter to 2 liters. It means that the variable that you're going to control is volume. Then you have to change this variable to volume. So it means that we're going to use that trick that we just saw. Sorry, the other way around. What should I do here? Here. So we have to replace dp with partial p partial v times dv, such that we can use this as our variable. And that will be the same over here. It's going to be minus alpha v, and then so depending on what kind of variables are given, then you're going to have to replace that with suitable integration variable such that you can calculate. Okay, we'll stop over here and then come back to the calculation later. So let's go back to this problem. So we wanted to calculate the change of Gibbs free energy and the change of entropy for this van der Waals gas. And of course, we already know for van der Waals gas, we have this expression, and the problem tells you the number of A and B, of course, and you know the gas constants are. So in fact, you can calculate this directly if you know the expression of V and if you know how to do this mathematical trick. However, doing this is kind of complicated because we'll see that on the next slide that for van der Waals gas pressure, if you move these terms to the right-hand side, it's expressed like that. And therefore, if you want to calculate this, it's kind of messy. So let me do this using my own cheat sheet. So follow this this trend. So we know that Eg is VdP again. This is V times because the constraints given are volume 1 and volume 2. So it means that we have to change that to dV. So if you follow textbook, it actually asks you to calculate dP first. And dP seems to have two terms, and there's one term related to dV, and there's also a term related to dt, because if you take the perfect differential, you need to take this one first and then this one. So it seems to be more complicated. But in our case, if we use this, it's actually more straightforward. Because now we know that what we want to calculate is partial P, partial V. And later you'll see that it is this term, right? Because that is dP over dV. So that's the term we're going to figure out. But since P is minus A over V squared, so this is pretty straightforward, right? You take the derivative against volume, and temperature is a constant here, so you don't have to worry about that. It's just a coefficient. So it turns out to be minus RT V minus B squared, and this is plus sign 2A V to the 3. So actually, if you know this, then you can plug this back in to do the calculation. And you can also use that to calculate this one, right? As long as you know alpha further, then you can calculate that. So this is the logic for textbook, although the expression seems to be more messy, okay? So if you want to forget about that, it's also fine. You can just follow this. Seems to be more straightforward. And so to calculate that, dg, so you basically plug this back in. Let me just summarize that. It will become 2a. I also move this term to the front over v squared minus VRT v minus b squared dv. So this is your sort of final expression to calculate delta G, because you know what A is, and you know what VRT is, RT is, and all the variables are just, for instance, volume is the variable that you're going to integrate over, so you can calculate that. Of course, if you do this numerically, like if your calculator can directly calculate these terms, then it's pretty straightforward. But if you want to calculate that by hand, you have to do some mathematical trick. So here, say this is from volume 1 to volume 2, which is 1 liter to 2 liters. 2a. Let me rewrite this first. And this term is a little bit harder to calculate. So typically we'll expand this. We'll put a v minus b here and then have a plus b back. So this will become RT square and plus something back, and we'll have a minus sign, so this is minus BRT square. Okay, so this is the final expression that you're going to use to integrate over this range of volumes. And the reason why we decompose this one into two terms is because if you decompose this, then this is integrating over v minus b squared, and this one is integrating over v minus b, inverse of v minus b. So you expect RT log v minus b. So this is it's a minus 1, minus 2a. Sorry about that. Minus 2a over v. Because originally it's minus 2 over here, and then it turns out to be minus 1 here. And also the order is v minus 1. And then we plug in this. And minus RT log b. And this is also pretty straightforward. This is plus RT. That's it. So once you know what V2 is, V1 is, you should be able to calculate the number. Okay, and the textbook actually gives you a number which is, I think I have it here. But we don't know if this is correct because in textbook, if you still remember, like I said, there's a squared here. It uses a squared instead of a, which I think is incorrect. But throughout the calculation, the textbook still use a squared, which I think is wrong. So the number maybe is not that correct. So if you want to do that numerically, so let's check. So I typically use Mathematica to check. Maybe this is not large enough. Let me zoom in. So how many of you have Mathematica? No? I mean, it's a software which allows you to, I mean, it's a paid software, it's not free, so I can understand. But it's very common to use to do some symbolic calculations, also integration. I believe that you probably use Wolfram Alpha to integrate a lot of things in the past. It's an online integrator. But this is the software part. You can define the terms like A, B, and like the temperature and the gas constants. And we want to calculate the change of Gibbs free energy, so you just integrate this over what I just derived. And let's calculate that. I think it turns out to be minus 2300 joules. You folks can check with a calculator later, to see if this is actually this. But I believe Mathematica can give us a very accurate result. And don't forget that we have to convert this into joules, because here the result will be in ATM times liter, so you have to convert that to joules. So I also uploaded this, I turned this into a PDF file and then uploaded it on Saba. So if you want to check, you can go ahead. So this is the Gibbs free energy part. Seems to be pretty straightforward. However, if you're going to calculate the change of entropy, it seems to be more complicated. Okay, it seems to be more complicated. Let me just show you the strategy proposed by textbook. So the strategy of the textbook is that we already know, like ds has this expression, right? And we also know how to calculate this term, like over here. So this is what we're going to plug in over here. Right? And we have a volume here. We'll save that. But more importantly, we need to know how to calculate alpha. So this is the isobaric expansion coefficient, thermal expansion coefficient of that gas. So we need to calculate partial V, partial T based on what we have. So what we have over here is that it's actually very complicated, because if you want to calculate partial V, partial T, you have to move all the terms that are related to a volume to one side and temperature to the other in order to calculate this. But nevertheless, the textbook shows you that there's a way to calculate it. And it is based on this equation. So what I skipped earlier when I calculate this is that for a textbook, it uses this like perfect differential. or you expand dp as a function of dv and also dt. So you have these two terms. You have this dt term, and you also have this dv term. And from these two, if you consider an isobaric process, it means that dp is 0 over here. This is 0 over here. Then you can estimate partial v, partial t, right? It is the ratio of these two factors, the ratio of these two factors. So once you know that, so once you know what partial v, partial t is, then you can calculate alpha. You can calculate alpha. So this is a fairly complicated task. So first of all, you need to figure out what alpha is. And more importantly, how to calculate partial v, partial t. But let us just assume that you know how to calculate that. And then the result will be something like this. It's kind of complicated. So it's having a minus sign. Let's say it's v to the 3, v minus b square hope this is correct. So anyways, it's a complicated term. And after you finish this calculation, you plug this back in over here. And of course, we know that there's a volume here that will be canceled out with this 1 over v. So this part will be eliminated. So you're left with this and a minus sign, and the minus sign will be canceled out with this one. So you're left with just r over v minus b times this factor. And later we're going to use this factor as well. But then you'll realize that there are a lot of the terms can be canceled out. For instance, we know partial p, partial v at a constant temperature is like this. And this happens to be exactly the same as the inverse of this one. So you create a lot of messy terms, but then it turns out that when you plug this back in, they'll all be canceled out. So this is the strategy of textbook. So you plug all those things back in, and it turns out that delta S or ds is simply that expression. So it means that there must be a way to eliminate this messy calculation. Okay, but also, like if you follow textbook, there are also some typos there. So on page 262, you'll see that, let me write over here. You'll see that there's an equation stating that right, if you can locate this one, so this is a typo. There's no equal sign over here. So I don't know why there's just a typo there. So it's this one with the line above, they're the same equation. They're the same line, but they put an extra equal sign over here. So this is a typo that you probably want to remove. Okay, so let us talk about the more straightforward way to calculate ds. I will maybe just eliminate this. And actually, it's very straightforward. And as long as you know some tricks, especially what you learn in chapter 5, this will become a very simple task. We know that we want to calculate ds, and this is minus alpha v like this, right? And again, this is the reason why we have this is because we want to use volume as our variable for integration. And if we directly put alpha back in, this is simply there's a minus sign over here, this minus sign, and alpha v is simply partial v partial t at constant pressure. So once you see this, if you're familiar with all those mathematical tricks that we learned in chapter 5, this is the time you use this, what's this, upside, downstairs, whatever function, whatever trick that you have. So recall that. If we have this, and this is t, this is p, then we have what else? Partial v and partial t, partial p. And this is constant volume. Remember that if you have like 3 variables, and if you put them together, I mean, you can write down this equation. And we proved this before in chapter 5. So if you know this expression, you know that minus 1 times partial v partial t at constant pressure and partial p partial v at constant temperature is simply partial t partial p at constant volume. So basically, you can replace this with a minus sign, to this. Sorry, reverse. Partial p, partial t, yeah. So it turns out that this ds is simply v times dv. It's this. And if you still remember, this is actually one of the Maxwell relations. If you move this to the other side, if you memorize those Maxwell relations before, this is actually one of them. Okay. So this is more straightforward after you have this, because you know that, again, let me rewrite this. The pressure is it's this one, right? Therefore, this is simply R over V minus B. Right, because this term is a constant, so just eliminate that term. So eventually you'll have this expression. And therefore, this is much easier to calculate. Okay, so eventually, delta S is simply just R log V2 minus B over V1 minus B. So I'll suggest that you still go through what textbook says. And you'll realize this mathematical trick is very useful, such that you can just directly convert all these into a very simple form, and then just calculate the result very easily. Otherwise, you have to go through all those weird calculations. Like you have to derive alpha explicitly first, right? And then later on realize that you can actually cancel out. And the reason why you can cancel out is because this conversion, because we know that these two can be eliminated. There are a lot of terms can be eliminated. But if you calculate that early on, like if you derive those this explicitly in the early stage, you have to you need to deal with a very messy calculation. But if you start from this simplification at the very beginning, then you only need to calculate this eventually. And like I mentioned earlier, this is one of the Maxwell relations. If you still remember that, this is the starting point. Like if you want to calculate like partial P, partial T, and relation with ds and dv, this is the Maxwell relations that you're going to start with. Okay, so if you plug in and do the numerical calculation, actually this is much more straightforward, and you can calculate the delta S much easier. Okay, so this is the numerical examples for this chapter. And there's this second example, which is more straightforward. The second quantitative problem is that you have to calculate delta G for a certain virial gas. And in that case, you just follow this expression, and then you can calculate things numerically. Okay, so the second problem is way more straightforward. So I'll leave that to yourself. Let's do this. Okay, so for the final part of chapter 8, we're going to talk about mixtures. In the 6th version, like if you're using, again, the new version of your textbook, this is actually the very beginning of chapter 8. But I think the older version is better because you're going to learn more about mixtures in chapter 9 or for the next semester. So it's better to arrange this part at the end of this chapter. Okay, so for a closed system, not sure if it's on. We're going to wait for that. For a closed system, we already know that dg is vdp, okay? And therefore, if you're dealing with ideal gas, you can do this conversion to RTD log P. We already know that. We've already seen that several times. So if your system is going through a constant temperature process, and then you change the pressure, you have this evolution from P1 to P2, then the change of Gibbs free energy is just RT log P2 over P1. Right, or V1 over V2 if you're changing the volume, or the variables given. If the variable given is volume, then it is V1 over V2. You have a sign change. And for this part, we're going to establish the standard state. I'm not sure why that is not on. The standard state means that the condition where you're dealing with is at 1 atm of pressure. So if you're dealing with 1 atm of pressure, typically we'll put a 0 on the upper right hand of the Gibbs free energy, which means that it is the condition where the pressure is at 1 atm. I think it's not on. Maybe gradually. Just wait for a bit. So eventually, the Gibbs free energy is the standard Gibbs free energy plus this RT log P, right? Because you're calculating the change from 1 atm to a certain pressure P. And we know that log 1 is 0. Okay, log 1 is 0. So eventually, this is an expression that you typically will see. Okay, so it's up. So G naught, which means that this is the condition at 1 atm. And if you change the pressure to some certain value, this is the difference that you will see. Okay. And another concept that we're going to introduce is mole fraction. Like for instance, if you have a bunch of different molecules confined in the same box, and we want to figure out what's the fraction of that certain gas, then we'll use a small fraction. So this is a very basic definition that you have several different kinds of particles or molecules, for instance, A and B and C. And if you want to calculate the fraction, you use these formulas to calculate that. And of course, if you sum all these fractions up, it will just become 1. Okay, so these are pretty straightforward. More importantly is the concept of partial pressure. Okay, because typically when we talk about pressures previously, it seems that we're only dealing with just one pressure, right? For instance, over here, just one pressure. But if you're dealing with a mixture of different kinds of particles or different gas molecules, actually there's this fraction of pressure that you can use to calculate a lot of different things. And that is called the partial pressure. And Dalton's law of partial pressure states that the pressure exerted by a mixture of ideal gas is equal to the sum of the different pressures exerted by each of the individual component gases, which means that if you have, for instance, in the case of having 3 different kinds of molecules, A and B and C, then it means that PA plus PB plus PC should be the total pressure. Okay? So there's this definition of partial pressure, which means that the partial pressure is smaller than the total pressure, and it somehow can represent the behavior of each gas molecules in this combination. So the partial pressure exerted by a component gas, Pi, notes that we use this small p instead of the capital P here. So Pi is the pressure that it would exert if it alone were present, which means that if we only have this, for instance, we have A, B, C, and if we only have gas A in this box, then the pressure will be PA, for instance. The concept seems to be weird at this point, but we'll see that more clearly later. So consider a system containing, for instance, Na moles of A, of course, and you have the same representation for B and C. Then what I just stated using words can be represented by an equation like this. The total pressure is PA plus PB plus PC. So consider a fixed volume V prime. And the reason why we have prime here because volume is an extensive property. So typically in this textbook, for extensive property, you put a prime over it. Let me find this. Sorry. So if you're not familiar with partial pressure, I'll suggest you just draw a picture. first. So consider, so this is a fixed volume, let's say V prime. And you have different kinds of particles like A and B and C. Different kinds of particles. And we wanted to see that, P, this is capital P. Let me write this bigger. Is something like this. But if you only consider particle A, we know that ideal gas law should still sustain. So that's the reason why the total pressure P is actually NART over the total volume V prime. So this, remember that this is a fixed quantity, this V prime, which means that the volume is not going to be expanded or changed by adding gas molecules into this box. So this is a fixed, let's say this is a fixed container. So you suddenly realize that this Na is related to V prime and P through this ideal gas law. So this is a case, let's just imagine that the only particle A is in the box. Consider the case that when you have two kinds of particles, so you have A and B. So you have A and B in this container. So the total pressure, let's say, is still, this is P, but this P is actually different from the original P over here. Now the pressure is PA plus PB because based on the definition of partial gas, we have contribution from A and contribution from B. So it turns out that you have the original expression, like NART over V prime, and a second term that is related to B, which is NBRT over V prime. And of course, if you combine these two together, you'll see that it is NA plus NB times RT over V prime. So this is still the same as this one, right? Because this is a case when there's only particle A in the box. But if you have two different particles in the box, you have to use Na plus Nb. So this is very straightforward. And you should expect a different kinds of pressure. So don't be confused by the P notation of capital P over there. This P is different from the previous P. Okay? So when you have two different kinds of gases, you have this expression. Since we know that, for instance, the temperature is the same, V prime is the same, of course R is a constant, but now you have Na plus Nb, so you know that this pressure will be different from this one. In that case, we know that this is PA, right? This is the original P. So I would say this is, let's say this is P tilde. Recall that P tilde does not equal to P, and P tilde equals to PA. Okay, so these are just some sanity check to verify that what we define is okay. So if you add like NC, like if you add another kinds of particles in, then you know how to do that. You have to add another term, and in that sense, that total pressure is also different from the original pressure. Okay. So if you divide equation 8.13 is this one by 14, which means that you divide these two if you divide these two, you'll see that PA over PA plus PB is NA over NA plus NB. Therefore, the partial pressure, the PA, is simply the total pressure times the small fraction, which is sort of pretty straightforward, right? Because if you want to consider the contribution of one of the gas molecules in the system, is simply the total pressure times its small fraction. I believe most of you learned this during the freshman year chemistry. So this is, just a review for that. And then starting from the partial molar, for instance, the partial pressure, we also switch gear to talk about partial molar quantities. And the molar, it means that the molar value of any extensive state property of a component, of a mixture, and this is called the partial molar volume, partial molar value for that certain property. One of the examples that we saw earlier this semester is the partial molar Gibbs free energy, right? And we proved that the partial molar Gibbs free energy is the same as the chemical potential of that certain species, like partial G, partial N. That is related to mu I, right? If you still remember, the partial molar Gibbs free energy for certain species is the chemical potential of that species. So that's one example. And partial molar quantity of a component is not necessarily equal to the value of the molar property of the pure component. So this is slightly different from what we saw earlier for the pressure case, right? We saw that the partial well, we can say the partial molar pressure or the partial pressure are the same thing, but this is not a case for any kinds of quantities. So for instance, partial molar, let's say Gibbs free energy, is not necessarily equal to the value of a molar Gibbs free energy for the pure component. So it's not necessarily the same thing. Well, it depends on how you define these things, but this is we don't assume that the partial molar, for instance, Gibbs free energy is the same as the molar Gibbs free energy. Okay. And it is related to, for instance, the interaction when you mix different things together. If they have some interactions with each other, for instance, you are dealing with non-ideal solutions or non-ideal gases, then the partial molar quantity will not be the same as the partial quantity. So let us just consider a generic extensive property called Q prime. Then the partial molar quantity Qi prime means that it is partial Q prime over partial Ni. So for instance, if I'm dealing with Gibbs free energy and this is extensive property, we'll say let me erase this. And you can say T and P and for all n subscript, which is if the index is not the same as I, then you have to fix them, and also temperature and pressure. So this is the total Gibbs free energy over partial Ni, and that will give you the partial molar quantity or the partial molar Gibbs free energy of that certain component, right? And this is just one example, and previously we know that this is the same as the chemical potential of that certain species. And therefore this Qi bar, for instance here is Gi bar, It's a rate of change of that quantity with the change of the particles you add into the system at constant temperature, constant pressure, and also the composition of the rest of the mixture. Okay, so it is similar to, like, for instance, if you're adding 1 mole of some certain species into the system, what will be the change of this extensive value, right? So this is the reason why we call this a molar change. So if you use Gibbs free energy, and this is what you will get. The chemical potential will be the same as GI bar. And the partial molar Gibbs free energy of a component in the mixture will be the same as the chemical potential of a component in the mixture. So this is what we just wrote down. And if you recall that, we know partial G, partial P is a volume. And if you consider this G prime, this is the Gibbs free energy of the whole system. If you take that derivative against pressure, you'll get the volume of the whole system, which is V prime. Remember, the box of that gas molecules, it's V prime and it's fixed. And if you further take that derivative against Ni, which is we want to consider the molar change when you, for instance, adding that certain species into the system, you'll end up with partial V prime, partial Ni. And by definition, this is the partial molar volume for that species, right? This Vi prime represents the partial molar volume for species I, Okay, so this is from the definition of Gibbs free energy, and you know that partial G, partial P is V. So you can derive this. And we know that Gibbs free energy is a state function. Therefore, we can change the order, of this partial differentiation. And therefore, if you do that, previously we do partial G, partial P first. But if you do partial G and partial N first, the result should be the same. Therefore, we know that the partial Gi bar, which is the differentiation of molar Gibbs free energy against pressure, should be the same as partial molar volume. Therefore, you have dGi as Vi bar dP. So the bottom line is that originally, throughout this chapter, we use this equation a lot, right? dG is V dP. And when we talk about this, we're always talking about just one component system. But if you're dealing with a system with a mixture of different kinds of particles, then it turns out to be simply putting a bar over here, which represents the partial molar quantity. And we also use that partial molar quantity for volume. But more importantly, this dP is the same. So the dP here is not partial molar pressure or what other kinds of pressure. It is the pressure of the whole system. So this is the how would I say? This is the thing that we probably have to remember, that when we derive all those things, we're taking the derivative against the whole the pressure of the whole system instead of the partial pressure. So we only see bars over here and here instead of over here. Okay, so the P here, you can say this is the same. The only change is this part and this part. Because we cannot take the molar fraction for both these two terms. Only one of these two will have this partial Ni being taken. But in this expression, we absorb that into this volume part. Okay, so this is what you use frequently I think next semester. So consider if you have just ideal gas A in the mixture of the case that we mentioned earlier, you have A and B and C, then this, you can just put this as A. Then dGA bar will be VA bar times dP. Later we'll come back and see like what's the correlation between this VA bar and the total pressure. Okay, we'll just stop over here first. Okay, so the molar quantity, at least in this case, what we're talking about is partial molar volume. And we saw that we wanted to express this dGA as VA times dP, right? And note that we focus on this VA bar, and we say that dP is the same. I mean, this pressure is the same as the total pressure, right? So this is not a molar or partial molar pressure. So in order to include the partial pressure, we need to do some tricks. So let us look at this definition of partial volume, VA bar. So in this gas mixture, this VA bar is essentially the same as the total volume divided by the total mole in the mole number, of the gas molecules in the system. Because remember, if you add 1 mole of a particle A into the system, there's a slightly change in terms of the volume. If that's the case, then that's VA bar, right? If that's the case, that's VA bar. So this VA bar is actually the same as VB bar and VC bar. They can be represented by the total volume over the total mole numbers, of the system. Okay, and therefore, if you do that, so VA bar is the same as the total volume over the total number of gas molecules in terms of mole numbers, in the system, and or in textbook, it is represented as the summation over like NA, NB, and NC, or simplified as summation over NI. So right now we want to take, because like I mentioned earlier, here we have the total pressure. We want to see what we can do if we want to use partial molar pressure to calculate that. So note that the partial pressure that we learned earlier, for instance, for particle A, so it is small p and capital A over here, is NART over the total volume. Okay, so over the total volume here. Which means that if we want to replace total volume, we can use this NART over PA. So you start to see like where the partial pressure can play a role here. So VA bar can be replaced by, this is, we keep this term over here. So this is a summation over all particle numbers. And here we have NART over the partial pressure for particle A. Okay. And recall that this is, here, if you have NA over like NA plus NB and NC, this means that this is the molar fraction of particle A. So it turns out to be XA RT over PA. So this is another way to express the partial molar volume or partial volume for particle A. So if you plug this back into here, so VA bar is XA RT over PA dP. And recall that this is the capital P, the big P. So the pressure of the whole system. And you can also express this using the the molar fraction. So dP, I mean, we know that PA, the small PA, is XA times P. So let me write over here. So this is, what's dPA over XA, right? Because we know that PA times XA will be, like PA will be the capital P times XA. So you have this conversion. So if you write these two together, it will become, let me, what is this? A times so it means that so the strategy here is to replace VA bar with something that is related to partial pressure and the molar fraction. And for the pressure of the whole system, we also do the same trick to represent this term using the molar fraction and the partial pressure. So it turns out that these two will cancel out. So you are left with RT d log partial molar, the partial pressure of particle A. Okay, so the change of Gibbs free energy, partial molar Gibbs free energy, is RT d log partial pressure A. I think in the next semester, when you encounter this again, typically you'll just memorize this. And if you compare this to the original form, if you still remember, for ideal gas, you have this, right? So it's almost the same, except that now you're dealing with just like partial molar pressure, like G bar for certain species, and you use small p, and you use pi. Okay, so this is pretty straightforward, although the derivation seems to be complicated, but the result is pretty straightforward and let's say it's pretty elegant. So if you integrate this between the limits of 1 atm to a certain pressure, then you'll retrieve this equation, because typically we want to see like how the Gibbs free energy change against the standard, against the standard condition. So for certain species A, GA bar will be GA0, which is the this quantity at 1 atm. And because if you plug in 1 over here, this is 0. So you're left with just RT log PA, which is the pressure change, the final pressure. And we know that PA can also be decomposed into these two terms like XA and P. So you can also write this as these two terms. Okay, so depending on how much how many particle A you include in your system, the XA can be changed. It can change from 0 to 1, right? We know that the maximum number for X will be 1, because it means that the whole system is just this particle A. For instance, if XA is 1, then this term is 0. Right? This term is 0. Then you're just having GA bar is GA0 plus RT log P. Okay? But if you have some other particles in the system, then you have a negative number over there, for the second term, on the right-hand side over here, because XA is typically less than 1. So this is typically, this is always a number that is less than 0, which is negative. So we typically use this expression to discuss the heat, or you can say the entropy change for mixing of ideal gases. For instance, for component I, this is a general form. GI bar is GI0 plus this RT log Xi plus RT log P. And we know that Xi is something that is less than 1. Again, so this is something should be negative unless Xi is 1. If Xi is 1, which means that this term is 0. Okay? And if you divide this Gibbs free energy by temperature, and then differentiate this with respect to temperature, then we have this form. And this is the reason why we do this is to use the Gibbs-Helmholtz equation, right? If you still remember from the end of chapter 5, I think chapter 5, we derived this Gibbs-Helmholtz equation to connect Gibbs free energy to enthalpy. So if you use Gibbs-Helmholtz equation, you can connect these two, Gibbs free energy and the enthalpy. So since right now we have two Gibbs free energy, we have Gi bar, which is the partial molar Gibbs free energy, and this is the standard state, Gi0, at 1 atm. So if we do this differentiation, these two terms will be eliminated because these are not temperature dependent, because once you eliminate one temperature, so you have Gi bar over T, so you've already eliminated that factor of temperature over there. And therefore, this term is actually temperature independent. If you take the partial against that, you're only left with just Gi bar, right? You're only left with Gi bar. And for the right-hand side, this is only Gi0. So it turns out that if you use Gibbs-Helmholtz equation to relate these two, it will give you this relation. The Hi bar, the partial molar or the partial enthalpy, molar enthalpy will be the same as Hi0. The component, the enthalpy of that component at a standard condition. Okay, so this is just one thing that we derived. The partial molar energy of ideal gas for some certain species I and a mixture of ideal gas equals to the molar enthalpy of pure I, which means that during the mixing process of this ideal gas, there's no change in terms of enthalpy, right? Because before mixing and after mixing, they are the same. So there's no change in terms of this enthalpy when you mix these bunch of ideal gases. But this is only the case for ideal gas. If you're dealing with non-ideal gas, the result will be different. But in this chapter, or at least in this example for this derivation, we only focus on just ideal gas. So in this case, we'll see that the change of enthalpy for mixing will be 0. Because before and after, this is before, it's Hi0, and after it's Hi bar, they are the same. So in this case, the change is 0. But this is only the case for ideal gas. If you're dealing with non-ideal gas, they have some interactions. So it turns out that delta H mix is not 0. Okay. So the philosophy here is that since Gi0, it is Gi0 temperature, and Hi is Hi bar temperature, the mixing, for different kinds of temperatures, you'll get the same thing. It's not only at some certain temperatures. For different temperatures, you'll get the same thing. So the mixing can be conducted at different kinds of temperatures. And delta H mix is always 0 for ideal gas. Okay? And the reason is because the particles of an ideal gas do not interact with one another. So for the mixing, you don't gain any energy from that or lose any energy from that. And the Gibbs free energy for mixing of ideal gases, typically, like we wrote down earlier, the dGi is RT d log Pi. Therefore, Gi bar is Gi0 plus RT log Pi. And for each component of gas before the mixing, okay, before mixing, we know that the pressure is capital P. And Gi0 is the same because that's the standard Gibbs free energy when only that species is there. So the only difference is this small pi and capital Pi. So before and after, this is the only difference. And we want to see what's the change of Gibbs free energy before and after mixing. So let's assume that we have an unmixed state and it is evolved to a mixed state. So during this mixture, we know that there's no gain in terms of delta H, right? But let me remove this. We want to figure out what this is, but we already know that this is 0, right? From our previous argument, we already know that for ideal gas, this delta H mix is 0. So actually what we're left with is this entropy term. So if you still remember, the definition of Gibbs free energy is H minus Ts. And so for delta G mix, we know that delta H mix is 0. So what we actually are interested in is actually this term, the delta S mix. Let us assume that this is conducted at a constant temperature, so we don't have to worry about the change of this one. But this number is always positive, so it does not really matter. But the problem is this one. If you still remember from chapter 3 or chapter 4, we argue that for ideal gas, for a mixing process, delta S is always greater than 0, right? This delta S mix is always greater than 0, for mixing of ideal gas or ideal gases, different kinds of particles. So this is always positive, therefore delta G mix is always negative. We've seen this kind of argument earlier. So we're going to see that over here as well. So delta G mix or G prime mix, the prime here again means that this is an extensive property. So it's essentially the same as what I wrote over here. So if you want to put the prime here, it's the same. The delta G prime mix is, of course, the total mole number times these GI bar, because this is a partial molar Gibbs free energy, after mixing, minus that quantity before mixing. Okay? So it turns out to be NIRT log small pi over the capital Pi. So this is before, this is before, this is after, right? And after minus before. So we have small pi over the greater pi. Therefore, delta G prime mix depends on this small pi and large pi for each gases. So we know that before mixing and after mixing, this pressure will be reduced. Like if you introduce more gas into the system, of course the molar pressure might be reduced. So if this is a number that is less than 1, like this ratio, if it's less than 1, then it means that delta G is less than 0. Then it will be consistent with the argument we saw over here. And it also means that since this term is 0, then this minus T delta S mix is related to that sigma I N I, let's say RT log small pi. This is the greater pi. We know that this must be related to this one, right? Because delta H mix is 0. So if before mixing, this is a very generic assumption. The gases are all in the same pressure. That is, all the pressures are the same, like Pi, capital Pi, Pj, for different, or Pa, Pb, Pc, they're all the same. And the mixing is carried out at a total constant volume, such that the total pressure of the mixture, P mix, equals to the initial pressures of the gases before mixing, such that Pi over, this greater P is Xi. Then this can be simplified to NIRT log Xi. So it simply means that if we can consider this as Xi, then let's say pi over capital P. And this will be just xi. So delta G mix is NIRT log xi. Again, this is also a very common expression, or that you will see later, maybe next semester, and also similar to this one, like dGA bar is RTD log PA, and delta G mix. For mixing, if you consider the evolution of the whole system, you want to calculate this, and that is related to the molar fraction actually. So this is the example of the change of mixing Gibbs free energy, and we all know that typically xi is less than 1. Of course, it should be less than 1 because the maximum number for xi will be 1, will be unity. So log xi is always less than 0, which is a negative number, and it turns out that delta G mix is less than 0. So the mixing is a spontaneous process because the Gibbs free energy has been decreased. Okay, so please bear in mind that there are two expressions that are important. The first one is this. I'll write this down over here. And note that these are all for ideal gases. For non-ideal gas, you have to use different kinds of expressions. And recall that this is for the whole system before and after mixing. Okay, so this is what you typically would use for the for next semester. So the final part of this chapter is about what I just wrote down earlier. I just erased that. We know that delta H mix is 0 because there's no interaction among particles, so there's no heat involved. But of course, we know that the Gibbs free energy has been decreased because it's negative. So that term is solely coming from minus T delta S, from the mixing entropy. We know that the entropy change for this mixing process is positive, right? So you have a negative sign, therefore delta G is negative. So it turns out that delta S mix is this minus, this is minus T delta S mix. You can put a prime here. Therefore, delta S mix prime is minus log X I. Right? So that's the equation at the bottom. You sum over all the contribution from different gases. And we all now know that this log Xi is negative. Okay, so this is less than 0. But you have a minus sign here, which means that this whole thing is always positive for the mixing of a bunch of ideal gases. Okay. So, I believe that this is the end of this chapter. And of course, later you see that if you divide this by the whole, by n total, if you want to do that, you can also divide this by n total. Then you can eliminate, you can turn this into xi. So it will become, the molar change of this mixing entropy will be something like this. With a minus sign. So this is a probably more common expression that you'll see next semester because you also divide this whole thing by the total mole numbers. Okay, so this is another expression that you'll see frequently next semester, hopefully, if you take thermodynamics for next semester. Okay, so I think I'll stop chapter 8 over here, and I'll mention a little bit about what we're going to talk about next week. So for next week, we're going to talk about statistical thermodynamics. So let me review some of these right now. Let me turn this off. So when we talk about ideal gas, we derive something called the partition function, and also the multiplicity, right? And let me review. Let's see here. What we learned before is that we started from, what's this? So for statistical thermodynamics, we're actually dealing with the same three types of systems. We have the isolated system, we have the closed system, and we also have the open system. I recall that from the very beginning of this semester, we discussed the distinction and the differences between these three systems. For isolated, there's only there's nothing exchanged to the outside. Therefore, you're dealing with just, for instance, a bunch of molecules which are confined in a closed boundary, and there's no energy exchange, and there's no particle exchange. And for a closed system, we know that the energy can enter the system, but not the particles. So imagine that you have confined numbers of particles, and they can exchange energy with the environment. And for open system, then there's no certain restrictions, so the energy can go in, go out, and also the particles can be added into the system. So the variables that define an isolated system, the variables are actually number and the volume of the system, and the internal energy, or you can say the total energy of the system. But for the closed system, there's no clear definition of internal energy U. So you're dealing with temperature. Okay? So that's the reason why actually for closed system, typically when we talk about closed system, it is in contact with a heat bath or heat reservoir, such that you can have a good definition of what temperature is. Because this closed system, we're going to have energy exchange with a heat bath. So when we talk about closed system, typically it is, for instance, in contact with a larger system with a fixed temperature. Let's say this is a heat bath. And this closed system can exchange energy, with this heat bath, but the numbers, of the particles confined in this space or within this boundary is fixed. So n is fixed, or this is the variable that you're going to consider, and the volume, and also the temperature. So we no longer can well define internal energy, right? Because internal energy can be changed when you have energy exchange with a heat bath. For open system, of course, the temperature is a control, but we know that the number is now also a variable, something that can be changed. So the variables that we're going to use will be mu, V, and T, and mu stands for chemical potential, because chemical potential will determine the flow of particles coming in and out of the system. So this is the distinguishment between these three types of systems. And in the language of statistical thermodynamics, we typically call this microcanonical ensemble. And we call the closed system canonical ensemble, which will be the focus of next week. Ensemble means a collection of systems, and this is grand canonical ensemble. So these are just the terms that physicists typically use to describe these three types of systems. And if you still remember, when we talk about, when we discuss chapter 3 or chapter 4, when we talk about the entropy, so we started from a general expression of the phase space and the the multiplicity. And if you still remember, we tried to calculate this thing. This is microcanonical. So we have fixed, let's say, let's not use fixed. Let's say this is well defined. N, V, and U. And remember when we talk about the phase space, let's say this is P and Q. We say that for a microcanonical ensemble, if we have a well-defined energy, it means that for the phase space, the distribution of P and Q will be limited to this, let's say, shell, or you can say this region, such that the Hamiltonian of the total of the system is confined within this shell. Right? Because the internal energy, once it's defined, let us assume that there's a small, let's say, uncertainty, which allows that the P and Q can be distributed within this range. And the H over here is the Hamiltonian. If you still remember, this is Hamiltonian. And this is the function which describes the total energy of all those particles, right? And if you still remember, this H, QI, PI. So Q means the coordinates, and P means the momentum. And for the ideal gas case, if you still remember, it is let us assume that there's something related to what's the potential energy, or what should I use? Maybe U, or it's V tilde QI. So we have two terms. Hamiltonian is an expression for the total energy, and total energy consists of the kinetic energy and the potential energy. And this is the potential energy. And when we discussed, the case for ideal gas, we said that there's no contribution from the potential part because the particles, they don't have interaction with each other. So in that sense, this part is 0. So you don't have this for the ideal gas. So for ideal gas, we only consider the kinetic energy of all those particles, right? So it means that this is in the case of ideal gas, this function is only, this Hamiltonian is only a function of those momentums, PIs, not the QIs. But nevertheless, the Hamiltonian is still being confined within this small range. And last time we showed that to calculate the multiplicity, we calculate this. How do you say that? This multiplicity is if you still remember, we tried to calculate this one, right? And that's the reason why we consider this 3n dimension sphere. And because we know that in the case of ideal gas, this function spans a sphere in the 3n dimension. So we typically, if we want to calculate multiplicity, we want to calculate this one, and we know the confinement is actually given by the Hamiltonian. Okay. So this is multiplicity. But this is before the correction. Right? It's in the first midterm that we have to take the Gibbs paradox into account. So that's the reason why I put a tilde here. Because for multiplicity, you have to divide that. So the real multiplicity is this term over H3n times n bar. N factorial n over here, right? Because we have the quantum correction and we also have the Gibbs paradox that we have to take into account. So this is the, let's write this over here. So this is a dimensionless multiplicity. We know that multiplicity should be dimensionless, right? So this is the real multiplicity. And it is dimensionless. Okay. And the explicit form for that is something like this. And remember, this is the quantum correction. And this is from the the Gibbs paradox. And if you really look at this expression, you'll see that we know that Qi times Pi. So this is in units of, this is coordinates. So length, this is in length scale, and this is in the units of momentum. And recall that for Planck constant, h is, the dimension for that is x and p. Okay, so the units or the dimension for the Planck constant will be canceled out with the dimension for this integration over dqi and dpi. Okay, so this is indeed without unit, or you can say this is dimensionless. And more importantly, if we look at this expression, we'll know that this omega, or let's say omega tilde, this omega tilde represents the volume, or you can say that the area, in this case is area, of this, let's say the shaded area, right? It's the area of this shaded area. So it means that if we can normalize this, if we consider there's a uniform distribution of particles, or these phase space are occupied by this uniform distribution of the points of P and Q, then there's a density function that can express this distribution. And let us assume that distribution is uniform. Therefore, for microcanonical ensemble, there's a distribution function. This is the beginning of this, the handout that I uploaded on Sabre. So for instance, if we want to calculate the density of this occupation of the points within this region, it will be the inverse of omega tilde, right? Because this is how we count how many points are occupied within this region. So the density of that will be the inverse of that value. Okay, the inverse of that value. And more importantly, we know that this is a constant. So let us assume that this is a constant. So this is a constant. And this happens when your Hamiltonian is within that region. So this is when your Hamiltonian is within that region. And it will be 0 otherwise. Okay, it will be 0 otherwise. So this function is actually called a probability density function. Or you can say this is called PDF for a microcanonical ensemble. So this density function states that if your Hamiltonian is within this range, which means that your P and Qs are in this range, then the probability density function will be a constant, which is 1 over omega tilde. However, if your Hamiltonian is, for instance, much greater than U, for instance, the Hamiltonian is much greater than U, means that your P and Q points maybe are here or here or here, then it's impossible to go there, right? Because the probability density function is 0 if your Hamiltonian is greater than that. Or actually, we should state this in reverse. If your, let's say, the probability of this to happen will be 0, right? Because this is how we define this microcanonical ensemble. We have a very well-defined internal energy, which means that for all the particles in this system, the Hamiltonian, the total energy should be well confined within this range. Right? So it's impossible to have a particle over here or over here, or over here, or over here. Or if you want to plot this in 3D, so P and Q, and this function is rho, microcanonical ensemble, it will be something like this. Okay, so the height of this one is 1 over omega tilde. And this is the, if you view from the top, of course, this is a distribution. But if you plot this distribution function or probability density function as a function of P and Q, you'll see that when you're within this circle, or these two circles, you have a certain height. But if you go out, it will be 0. It will be 0. Or if you go into this circle, the inner circle, it will be 0. So the bottom line is that for microcanonical ensemble, N and V and U are well defined. Therefore, the Hamiltonian can only be inside this shell or this two boundaries. And the density function is typically a constant and is defined by 1 over omega. 1 over omega. So therefore, if you integrate, if you base on this definition, if you integrate this microcanonical ensemble probability density function throughout the whole phase space, this will be 1. Right? So that's the reason why we call this probability density function, because if you integrate this within a certain phase space, that will give you the probability of finding that kind of state within that range. But of course, if you integrate this over whole, the whole phase space, although only these regions will have the existence of possible states, if you integrate this over the whole phase space, this will be 1. Right? So, and we already know that, let's say this is a constant. And if you just integrate this part, this will be omega tilde. This is what we learned earlier when we talk about chapter 3 or 4. I don't remember. But when we do that, we actually spend a lot of time talking about how to integrate this explicitly, right? And in this case, for microcanonical ensemble, this is a constant, like what we did earlier this semester. This 1 times this probability density function will be 1. So by definition, this is 1 over omega tilde. Okay, sorry.
So this is the case for microcanonical ensemble. And recall that, sorry, once we have this, we will be able to calculate this thing, right? And this is a function of, again, n, v, and u. And last time when we deal with ideal gas, we first derive this, and then we calculate the entropy. So, and from here, we can actually connect entropy to other thermodynamic quantities and then later define some other relations. So for next time, we're going to talk about canonical ensemble, which means that U is not confined anymore, and instead temperature is the quantity that will be confined. So for next week, we're going to talk about that.